Okay. Okay, first of all, I want to thank the organizers for their invitation. This is my second time in India, which is a fantastic country. I'm very grateful. And second of all, I want to dedicate this talk to the memory of a very dear friend. He would have been very bored, probably doing any other thing and probably sleeping. So if you do any of these things, you would be honoring him. So I won't be mad. Okay. So I also want to thank Marcelo and Stefano because they gave many of the important definitions I will need. And the context in which I will be working is diffeomorphism on a compact manifold. Okay, I will call the diffeomorphisms like this, but I will also require that they preserve smooth volume form. Okay, so this will be the context. And well, I will explain what stable ergodicity is for me. Both Stefano and Marcelo have explained it, but let me state it because I have slight differences with their definition. It's subtle, you don't have to worry about it, but I will say that F is stably ergodic if there exists a C1 neighborhood such that if G belongs to this neighborhood and G is C2, then G is ergodic. It's a little bit annoying to define things like this, but the reason why we should do this is because if you take away this hypothesis, you don't know whether there exist examples of stably ergodic diffeomorphisms. There are no known examples where an open set of C1 ergodic diffeomorphisms exist. So we have to do this. Another subtlety is that I am not requiring that F be C2. So in principle, a stably ergodic diffeomorphism could not be ergodic, which is also annoying. But a generic stably ergodic diffeomorphism will be ergodic. So don't worry about it. We will be worrying about genericity. I will explain shortly afterwards what that means. Okay, so the question is, what guarantees stable ergodicity among C1 diffeomorphisms? So let me first introduce the reason why we are studying this. In 1995, Charles Pugh and Mike Shoup in Montevideo, in the first international conference we did in Uruguay, they stated this very vague conjecture that a little hyperbolicity goes a long way towards guaranteeing stable ergodicity. But how little hyperbolicity? At that moment, they claimed that most partially hyperbolic diffeomorphisms were stably ergodic, which in the C1 topology was eventually proven by Artur Avila and Sylvain Crevisier and Amy Wilkinson. But the conjecture is still open in the C2 topology. But in fact, I want to conjecture, I want less hyperbolicity. I want to claim that less hyperbolicity implies stable ergodicity. How less? As less as you can get. I have been conjecturing this since 2012. In fact, in dimension 3. And what does this mean? This is the metric entropy, but another way to state it is that generically, in the set of C1 diffeomorphisms, either you have a dichotomy, either all Lyapunov exponents You know what Lyapunov exponents are. They have been defined in Marcelo's talk and in Stefano's talk. All Lyapunov exponents are 0 almost everywhere, or you have stable ergodicity. I dare to say even more. Stable Bernoulliness. Which is they are ergodically equivalent to a full shift. Okay? What does generically mean here? Means dense G delta set. Okay? Dense G delta set. Generic. Okay? So you have a very strong dichotomy here. Of course, this is a conjecture. And I posed this conjecture as a problem to my student, Gabriel, in 2012. I killed him with this, with this problem. He still likes me. Amazing. And currently, it's a work in progress with Sylvain Grosvissière and Gabriel and I. We're working on this. And we're confident that this should be true. So, well, I killed my student with this. He struggled with this for years. But we discovered many interesting things together. And finally, we got that adding a hypothesis, we could get stable ergodicity. If you have an invariant expanding minimal foliation, expanding foliation, you know what that is. It's a foliation where the tangent bundle gets, the derivative expands more than 1. Minimal means that every leaf is dense, okay? So generically, if there exists an invariant expanding minimal foliation, then you have stable Bernoulliness. What is stable Bernoulliness? Same as stably ergodic, but here you have Bernoulli. Bernoulli means isometrically equivalent to a full shift, okay? And there's a difference, there's a subtle difference between ergodicity because ergodicity is a generic, is a G delta property. So if you have a dense set of ergodic systems, then they are generic. But Bernoulliness is not a G delta, it's not known, at least that I know, it's not a G delta property. So you could have a stably Bernoulli set diffeomorphism, which is not Bernoulli. What is interesting about this theorem, which I must stress it is in dimension 3, what is interesting is that it does not require partial hyperbolicity, okay? It does not require partial hyperbolicity. And in particular, we have other, I will tell you in a minute what I have. So we have a conjecture behind that is far from being solved. In dimension 3, generically, either all Lyapunov exponents are 0, or there is a hyperbolic minimal invariant foliation. By a hyperbolic, I mean either expanding or contracting, okay? This is not known. It's far to be known yet. And, okay. We have another more modest conjecture than my first conjecture, which is generically in the set of C1 diffeomorphisms, either you have an invariant expanding minimal foliation plus a magic periodic point, which I will explain later. This implies stable Bernoulliness in any dimension. So this is a sort of the first theorem with Gabriel, but in any dimension. The existence of this periodic point, I mean, you will have an expanding minimal foliation, say W, with dimension equal U. And so you add the existence of a periodic point, hyperbolic, with unstable index equal U. If you have that, then you should have stable Bernoulliness. This is what we conjecture, okay? The existence of an invariant expanding minimal foliation plus a periodic point with the same dimension as the minimal foliation should imply stable Bernoulliness, okay? Okay. So we have a second theorem which gets close to this, but not as close as we wish. We say that for a generic map, if we have an invariant expanding minimal foliation, I mean, let me say something here. We are proposing minimality as a new mechanism for stable ergodicity. Up to here, there are no many mechanisms to produce stable ergodicity. Partial hyperbolicity is one of them, but there are not many. And this is one which does not require partial hyperbolicity. We are proposing this as a new mechanism to produce stable ergodicity and what's more, stable Bernoulliness. So if F admits an invariant expanding minimal foliation and we have this magic periodic point which has the same dimension as the invariant minimal foliation, then in a C1 neighborhood, all C2 diffeomorphisms inside this C1 neighborhood contain a hyperbolic ergodic component. I will explain in a minute what this is, which is not all. If it were all, we would have stable ergodicity. It's not all, but it is essentially dense. I will explain shortly what is essentially dense and what is hyperbolic ergodic component. So what is ergodic component in this setting? There are many definitions of ergodic component, but I will use one, a set A, measurable set, positive measure. I will say that this set is an ergodic component for F if F restricted to A is ergodic. And I will say that this set is a hyperbolic if all Lyapunov exponents on A are different from 0, which will be constant since A is ergodic, F on A is ergodic, okay? So I have a big ergodic component. Well, I have to say what is essentially dense. Essentially dense, or the essential closure is all, is the same. So A is essentially dense if for every ball in the manifold, the measure of A intersection the ball is positive. So it's more than dense. It's dense from the measure point of view. If you have any ball, it will have positive measure of this set. So I would love to say that we are close to proving stable Bernoulliness, but being dense, we know that it's not the same as being all. So, but well, it goes in that direction. But this has very interesting consequences. As a corollary, we have that if we have an invariant expanding minimal foliation, and you have this magical periodic point, then the foliation is stably minimal. What do I mean by stably minimal? Here there are also subtleties. Stably minimal is if there exists a neighborhood, stably minimal for F is a neighborhood of F such that for all G in C2 in this neighborhood, there exists the analytic continuation of this invariant expanding foliation, and this analytic continuation is minimal. So all C2 closed, C2 diffeomorphisms, which are C1 closed, contain a stably minimal foliation, which is expanding. In particular, F is stably topologically mixing. Stably in the sense that only C2, C1 closed will be topologically mixing. Because we have this minimality will imply topologically mixing. But we have sort of strong topological hypothesis. So I want, my claim in this talk is to introduce the existence of an expanding minimal foliation as a mechanism to produce strong mixing properties, both from the topological and from the ergodic point of view, okay? And, well, I am aware that the existence of a minimal expanding foliation is something relatively strong on one hand, but on the other hand, it requires nothing on the rest of the bundle. Because partial hyperbolicity requires unstable, stable, and something in between, which is controlled. I only require unstable. Okay, to the unstable, I require much. But on the other hand, I'm spoiling the rest. So you have to give me that. Okay, so this is new in that sense. Okay, yeah.
So you don't get this continuation of foliation free.
No, you will get it for free generically.
Okay.
Because generically, this foliation will dominate another splitting, and this will imply the analytic continuation. Okay? So in general, you won't get stably minimal cannot be defined like that. You should be more careful. You should say there exists an analytic continuation and this blah, blah, blah. But in general, this will happen for generic. Sorry. No, but generically it will mean. Generically it will happen. In general, the existence of an invariant minimal foliation does not mean anything. It could disappear. But generically, the existence of an invariant expanding minimal foliation implies that it dominates it dominates another subbundle, and that also implies the existence of an analytic continuation. So here the genericity is the key of all. For them alone, well, you can get it, but you should add it by hand. If you add all the hypotheses by hand, you get it anyways. Okay.
When you say analytic, you mean that
there it will be unique. You will have a unique analytic continuation of this. This is essentially follows from the stable manifold theorem. Because you will have domination, and the domination will imply that. You have expansion plus domination. This essentially follows from the stable manifold theorem. This foliation, it's like an unstable foliation. Or each leaf is C1, but they vary Hölderlin. Okay, the regular, I mean, it's the integral of an expanding bundle. Okay, so why should I put this annoying point here? Because I would love to get rid of this. But if I got rid of this, I wouldn't be stating this silly theorem. I would be stating a much more important theorem because which is unknown, which is the strongest foliation of an Anosov diffeomorphism minimal? It's not known. Not generically. You don't know in general if this happens. This is for linear maps, it's known, but you don't know in general if the strongest foliation of an Anosov diffeomorphism is minimal. I mean, you have a two-dimensional unstable foliation of an Anosov, and suppose it splits into two subfoliations. The strongest one, you don't know if it is minimal. Yes, in dimension 3, it's not even known in dimension 3. So
that would imply ergodicity.
Pardon?
It would give ergodicity. It would imply ergodicity.
No, not necessarily.
Not necessarily.
No. If it is C2, yes, but for C1, you. But this is an unanswered question, so that's why we have to put this annoying point, because this is an open question and it's very hard. Okay. So I hope I have time to present the proof of everything. So let me introduce the elements we are going to use to present this result. First thing, I will go a little bit fast because you already are familiar with this, thanks to Marcelo and to Stefano. This I will call the non-uniformly hyperbolic set, or Pessin region, which is the set of points that have non-zero Lyapunov exponents. Okay? So this we know. Marcelo has also mentioned the stable manifold, the stable Pessin manifolds, which could be short or long. We don't know. We don't have control on its length or whatever if we are in higher dimensions. Okay? And the same with Pessin unstable manifolds. Rapidly speaking, the Pessin stable manifolds are the points that asymptotically approach in the future a certain point, and the other ones are the ones asymptotically approaching a certain point in the past. Okay? But since you don't have uniform expansion or contraction, this could be this will, in general, for C2 maps, it will be regular, that's Pessin's result, but they can be short, long, you don't have control on their size.
The way exactly you define it, you define it with the global manifold. So
yes, it's the global manifold.
The local ones that change the size. Right?
Yes, if you stay within a Pessin block, you have control, but I will leave it like that, because we are not getting into Pessin blocks here. And so this was introduced by Federico and Ali Tassibi and Raúl Ures and me, which is called the Pessin homoclinic class, and fortunately, it has been used in many places, and is sort of homoclinic class, like the ones that are defined in the hyperbolic setting by Sylvain. But these ones are for Pessin homoclinic classes. Let me show you a picture. These are the set of points whose unstable manifold transversely intersect the stable manifold of the orbit of some hyperbolic point. It looks ugly, but with a picture you will see it better. You have here, for those color-blinded, the plane is blue and the vertical lines are red. And the plane is the stable manifold of P, and the vertical lines are the unstable manifolds of X, of any X. So any X which non-trivially transversely intersect the stable manifold of P or of any point in the orbit of P, which we will be called the Pezin homoclinic class of P. Okay? This is a very important object. It is invariant, and it is what is called U-saturated, saturated by unstable leaves. Okay? Yeah. No. It's because I can draw in 3 dimensions. But it could be this can be defined in any dimensions. And the unstable manifolds have to transversely intersect this, but this in general could be higher dimensions. The unstable manifold could be 2, in a 3-dimensional setting. Thank you for this question, because it's important to clarify. I did that because I'm lazy, so I put for k equal 1 to 50, draw a line. But drawing a 2-dimensional thing would require more work. But it can have 2-dimensional things. Okay, and the same can be done for the unstable manifolds, and then you define the unstable Pezin homoclinic class, which would be seen something like this. Again, you could have something 3-dimensional here in higher dimensions. They don't have to have the same dimension, but they have to intersect transversely and non-trivially, okay? And this is S-saturated and invariant. And there it comes the element and why we can prove things. We have developed the following criterion of ergodicity together with Federico, my brother, and Ali Tassibi and Raul Ures, which says that if you have a periodic point and the F is C2, and both the unstable Pezin homoclinic class and the stable manifold Pezin homoclinic class both have positive measure, then they coincide almost everywhere. And it is an ergodic component, and it is part of the Pezin region, okay? So this is a very, I like very much this theorem because it allows you to identify ergodic components in sort of a topological way. You just have to identify the points that transversely intersect the stable manifold of a point or the unstable manifold of a point. And then you get an ergodic component. This is very much useful. And okay, this is the intersection of both, which we will call PHC. And this, remember, this will be a hyperbolic ergodic component. Okay? Okay, I don't know if I will have time to tell you everything, but a remark is that if you have a periodic point such that it is homoclinically related to it, all the points in its orbit, okay, all points in its orbit are homoclinically related, then, and if you have that the Pezin homoclinic class is positive, then this set is not only equal to the set of points that intersect the orbit, but the set of points that intersect P. This is a consequence of the lambda lemma. I will not explain it here, but it has as a result that F restricted to this is not only ergodic, but Bernoulli. This is a consequence of Pezin's theorem, which states that if you have a non-uniform hyperbolic ergodic component such that all iterates are ergodic, then it is Bernoulli. But all iterates are the same here. So all are ergodic, then it is Bernoulli. Okay? Okay, second remark is that if you have a periodic point and this Pezin homoclinic class has positive measure, and this is Bernoulli, then the unstable manifold is dense in this Pezin homoclinic class. This is not hard to prove. It's really not hard to prove. I leave you as an exercise. It's an interesting exercise. Not only is dense here, but it's dense on the essential closure of this. Well, the essential closure is the closure in this, well, you can imagine the essential closure. I have to speed up a little bit. So we have the following generic property. This generic property has a long history. It began, the first to state this generic property was Magnier in the 80s. Then it was proven by Jairowski 20 years later. Magnier stated a draft, and the draft turned out to be super difficult to prove, and Jairo proved it 20 years later. And then 12 years later than that, I found that this also was true in dimension 3. And I give that this because Magnier's and Jairowski's statement was either all Lyapunov exponent vanish or it is Anosov. In 2012, I found this statement of this, but for dimension 3. And 4 years later, it was proven by Arturo Ávila, Sylvain Crevisier, and Amy Wilkinson by different techniques. And what essentially says that you have a dichotomy, which is not as this, but it gets somewhat close. Either all Lyapunov exponents vanish or F is ergodic. There is a Q, but this Q is not our magical point, regrettably. But this is almost everybody, or almost everything. This spacing homoclinic class is the whole manifold. That is why it is ergodic. And the Ocelleret splitting is globally dominated. You have heard of Ocelleret splitting in Marcelo's talk, so he has saved me to introduce it again because it's too long. Okay, so I will make strong use of this. Look, here the dichotomy is either all Lyapunov exponent vanish or F is ergodic. But I am more ambitious than that. I want to prove all Lyapunov exponent vanish or it is stably ergodic. It's much more. So we have to require much stronger tools. Okay. So we are introducing the second. How long do I have? But that was 40 minutes, and I was told I had 45, so that is not the same. That's okay.
No,
that's
40 because it rings 5 minutes before. When it rings, it means you've got 5 minutes.
Okay. Okay. So let me introduce the blenders. The blenders were introduced by Cristian Bonatti and Lorenzo Diaz. Somewhere in, I don't remember the dates, but let me first give you, a blender is an open set where strange things happen. It's an open set which it comes from a certain hyperbolic periodic point and is activated by another hyperbolic periodic point which has co-index 1 and produces an open set where the stable manifold of this point behaves as if it had one more dimension. I will explain better what I mean by this. You have two periodic points, and you have this splitting, unstable, one-dimensional center, and stable, okay? And you have the unstable index of Q is one more than the unstable index of P. And then you are saying that this is a U blender associated to P and activated by Q. If every well-placed S+1 strip in the blender is an open set, okay? You have an open set where the following happens. If you place an S+U strip, S+U strip is a strip, is an S+U disk of this dimension. Well-placed is placed as in the figure, which is almost tangent to the stable manifold of Q. Then it non-trivially intersects the unstable manifold of P. You will try to retain all this information. I know it's hard. You will see it in the picture again in a minute. Not only this happens, but this is C1 robust. And the stable manifold contains a well-placed S strip in this unstable blender, okay? So you have the following thing. I will show you the picture again. You have an open set. You have a well-placed strip, S-strip of the stable manifold of Q. And so that every time you enlarge it a little bit in one dimension, in the center direction, it is transversely cut by the unstable manifold of P. All S+1 strips, which are well placed in this open ball, well placed means almost tangent to the S+1 tangent bundle, they are transversely cut by the unstable manifold of P. Blender is a complex definition. There are many definitions. I will use this. And essentially, Blender is a magical thing that makes what you want happen. And this is what I will want to happen, and I will explain you shortly what I want this for. So there are two magic things about blenders that I want you to remember. One thing is that generically, if you have 2 points of co-index 1, then you have a blender. Okay? You have a U blender associated to P and activated by Q. Okay? They exist generically. Every time you have 2 co-index 1 points, then you have a U blender. The second thing is that if you have a U blender associated to P and activated by Q, the unstable manifold of the smaller index P, the closure, covers the unstable manifold of the larger index. Okay? So that's why I say that the unstable manifold occupies more space than it should. Okay? This is the two properties of blenders that you should remember. It is a magic black box that generically exists and produces this thing. Okay. Now we have the other thing that I want you to see, which is super blenders, which is even more complicated, were introduced by Gugu and Zulu in 2012. And this is essentially the same thing, but to another level. You have the unstable manifold, the unstable bundle splits into K subbundles. And if you have any point in the hyperbolic set, we will call S a stable superblender associated to lambda. If every well-placed unstable K-strip, I did wrong in putting the same K. In fact, it should be L-strip because it can be any point in between. Any well-placed unstable L-strip cuts the stable manifold of one point in the hyperbolic set. Okay? So the hyperbolic set also behaves as if their stable manifolds occupied more space than they should. Okay? And this is C1 robust. So I will use both the blender and the super blender property. So I will have to choose which theorem to prove because I have 6 minutes. And I will prove the one that uses super blenders. The other thing that you also have to remember about super blenders is a hyperbolic set which is magical and it exists, generically. Generically, if either all Lyapunov exponents are 0 or else there exists a super blender. A super blender with associated to a hyperbolic set, and the stable dimension is that one of the magic, not the magical point, but the point of this theorem of the Avila-Crevisier-Wilkinson, such that PHC Q equals M. Okay, so proofs. I need this minimality criterion. The minimality criterion says that if you have an invariant expanding foliation, and for some reason all unstable manifolds cut transversely the stable manifold of P, and you have this P has the same dimension, and the closure of this point is dense, then the whole manifold, the whole foliation is minimal. This is not hard to prove. All leaves cut in a compact part, and then this compact part can be shrunk, and they all approach the orbit of P, and eventually they get minimal. It's easy to prove. I leave you as an exercise. But what is important is that you should only prove that this is dense, and then this will be minimal. Okay? Okay, so this is not important because I will not prove this part because I don't have time. I will not prove theorem 1. I want to prove theorem 2. So generically in our conditions, we have minimal expanding foliation. So since we have a minimal expanding foliation, at least one of the Lyapunov exponents are 0. Since at least one of the Lyapunov exponents are 0, we have that the Ocel-Edet splitting is dominated. So we have that this expanding foliation has an analytic continuation. Not only that, there exists this Q, which is periodic, and such that PHC Q is the whole manifold, and so F is ergodic. We all have that because of our Avila-Crovisier-Wilkinson theorem. And so we have the existence of this, but the problem is that this Q does not necessarily have the same dimension as the dimension of P. If they had, then we know that the unstable manifold of Q is dense, and we would have minimality because of the minimality criterion. And then we would have what we want, and then we would have much other things. So we don't have that, but we do have that there exists a superblender, because I have just stated so, a superblender with this dimension, the stable dimension of S. And so all periodic points of the same index are homoclinically related, that is by Abdenur and Crovisier. And in particular, this QG, Q is homoclinically related, generically, Q is homoclinically related to any point in the hyperbolic set. In particular, it is homoclinically related to one point in the hyperbolic set. And so this is stable under perturbations. So under perturbations, you will have this for a whole neighborhood. Okay? So on the other hand, all leaves of the analytic continuation of the unstable manifold, of the unstable foliation, will contain well-placed and stable U strips in the superblender, because it is minimal, but the perturbation of a minimal foliation is close to be minimal. Okay? So they all enter the superblender. They are not minimal, but they are epsilon dense, so they enter the ball. And so the superblender property holds. And that's all that I need now. We have one thing that I should explain, and I don't have time. This Hessing homoclinic class is invariant, positive measure. And I have proven that in that case, it is essentially S and U saturated. That means it contains all its stable and unstable leaves. When some set is invariant and positive measure, it contains all, and it's C2, it contains all its stable and unstable sets. So we have that this is essentially S and U saturated. And this is what I am going to use. We have this is homoclinically related to this. This belongs to this. And so since Q is homoclinically related to one hyperbolic point of the hyperbolic set, and all points in the same hyperbolic set are homoclinically related, they are homoclinically related to all. And so, in particular, all stable manifolds of the hyperbolic set are contained in the closure of the stable manifold of Q. This is by the lambda lemma. Okay? They are homoclinically related, so this is contained here, and this is contained here, and this is contained here because I already said that these are S and U saturated. So if this belongs here, all its stable manifold belongs here because it's S and U saturated. So I have that all stable manifolds of the hyperbolic set are contained in the essential closure. Okay? But now the superblender property comes in. All G leaves are well placed. And remember that all well placed leaves cut at least one stable manifold of the hyperbolic set. Okay? Remember I said that the superblender had that property. All well placed strips, U strip cut the stable manifold of at least one point in the hyperbolic set. But since this is the unstable manifold of G, here you have all leaves have a U strip here. So all leaves cut at least one point in the stable manifold of W lambda. So the unstable of the stable lambda is all. But now I have told you that this was SU saturated. So this is all. Because it is stable by superblender property, this cuts all. By superblender property, by being close to minimality, all U strip get into this ball. And then they cut this, and then this is this, but this is US saturated, so this is all. And so we have U saturation. And, well, I don't have time to go on. I have just proven one part. The rest of the part it should be minimality. I don't have time to prove it. I use Blender's properties. I do a cascade of blenders, and then I prove that this is contained here, and then the unstable manifold of P is M, and this proves also stable minimality. I'm sorry, my time ran out, so this is all. Thank you. 谢谢。